Okay, question 5 here is hard. So we're going to prove this is true. So n plus 1, n plus 3, then you're multiplying terms through to 2n minus 1 and 2 times 2n will be equal to the power of n times the product of the odd integers of through to 2n minus 1. It's really not a fun one. But again, try to go, again, you got to do your best with your algebra and your steps. So n is equal to 1. So put in 1 there. 1 plus 1 is 2. 2 to the power of 1 times 1. The first term there. So 2 is equal to 2. It's true. We assume it's true for n is equal to k. So k plus 1, k plus 3, 2. K plus 2k minus 1, 2k is equal to the right hand side. So, come on, we're requiring to prove this. This is what we want to get. We start with our left-hand side and get to 2 to the power of k plus 1. 1 times 3 times 5 times, and the dot 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 through to 2 lots of k plus minus 1 and 2 lots of k plus 1. So, we start with our left-hand side. So, the k plus 2, k plus 2k minus 1. So, we go through to what n was equal to k plus 1, so we end up with that all the way through. So what's missing from the first step when we want to do the substitution is that we need to get a k plus 1 in there, because we've got that part there. We want a k plus 1 in there, and then we've got a 2k plus 1 and 2 lots of k plus 1 there. So to get the k plus 1 in there, though, we do a little trick. We're going to multiply by k plus 1. We're going to divide by k plus 1. We could just rearrange that and say, well, that'd be 2, and it's lots of k plus 1, so move that at the front. That's okay, but because this k plus 1 will cancel there. But we've got what we had in our step 2. So the k plus 1 through to the 2k. So we can make that substitution. And we've got 2 lots of k plus 1 times 2. So we bring our multiplied by 2 at the front and get 2 lots of 2 times 2 to the power of k, which gives us the 2 lots of k plus 1. And the 2 lots of k, because it's all multiplication, just can get absorbed into that bracket and gives us the 2k plus 1 at the front and in the bracket there, which means we have proved what we needed to. That's on it. Have a look through and work out, like, look at the tricks we've done, multiplying by the k plus 1, divided by the k plus 1. So you could have shuffled around. But have a look at that algebra. It's not easy. From 1998 HSC, we've got induction, proven by induction that 4 to the power of n plus 14 is a multiple of 6. So this one a little bit more straightforward. So 4 to the power of 1 plus 14 gives us 18 divided by 6 equals 3. Multiple of 6, beautiful. Assume it's true for n is equal to k. So again, we'll manipulate. We get the 4 to the power of k plus 14 over 6 equals m. M's an integer, so 4 to the power of k is equal to 6m minus 14. They're not pretty numbers. So we start with step 3 for k to the power plus 1. 4 to the power of k plus 1 plus 14. Again, break down, do a decomposition of our indices, 4 lots of 4 to the power of k, so we can get the 6m minus 14 in. And then we get 4 lots of minus 14 plus 14 would be minus 3 lots of 14, which we can break down to 6 lots of 7. And we've got the 24m out the front all the time, and which is divisible by, both are divisible by 6, and thus the whole thing is divisible by 6. Not too bad manipulation, but again, be clever with your manipulation of your algebra and your indices, your arithmetic, just so you can make sure you can get down to getting your factorization. Again, you want to do it as quick as possible, so you've got to be really clever with your algebra manipulation, your arithmetic manipulation as well.